Welcome everybody to the first edition of the SIAM-IMA Dublin Area Student Chapter Journal Club. My name is Edward Donlon. I'm a PhD student from TU Dublin and I'm also the chapter treasurer. And today we're going to be discussing a paper published in 1998 by Lagaris, who's the main author, on artificial neural networks for solving ordinary and partial differential equations. What's going to follow is the live recording that we did earlier this month, followed by some additional material that we covered in the subsequent discussion.
Right, let's get into it. So if anyone doesn't know about us, we're a student-led chapter aimed to foster scientific exchange and collaboration in applied mathematics and computational science in the Dublin area. All Dublin universities are welcome. I think we have people here from TU Dublin, UCD, Trinity, probably not DCU, but maybe in the future. So we're aiming to start this student journal club. This is the first time we're doing it. We just decided to work with work we found interesting, appealing, anyway exciting. If you have work interested in mind, we'd say get in touch. This is kind of stuff that we don't usually do research on, so this isn't my main research either. So I will do a bit of a forewarning that there probably is gaps in my knowledge here. So this is supposed to be more of a discussion than me trying to defend someone else's work. We're going to do about 15 minutes of a presentation and then 30-ish minutes of a discussion. So the discussion is the more important part than my presentation. And questions welcome. I'd say if a question comes to mind as I'm going along, put it in the chat. And feel free to make some kind of contribution at the end. I think as well, we could probably share in the chat our social links if people don't know them, our Twitter, etc. as I'm going along. Right, so here's a quick overview of the paper. This is what they do in the abstract. It's very succinct. We have a method to solve initial and boundary value problems using artificial neural networks, right? So artificial neural networks are the bread and butter of machine learning. They've been used in nearly every aspect of what you use computers to recognize things, or they're so universally applicable that they've been used nearly everywhere. And I'll come back to that idea of them being universally applicable. Now, the idea that they came up with was you compose what they call a trial solution to the differential equation, which is written as the sum of two parts, right? The first part satisfies your initial conditions or boundary conditions, depending on whatever you want. They have lots of examples in this paper of ODEs, PDEs, systems of ODEs, systems of PDEs. So they're saying this is generally applicable in pretty much any case you want. First part satisfies the initial conditions and boundary conditions and contains no adjustable parameters. And the second part is constructed in such a way that it won't affect that first part. So you're still going to satisfy the initial conditions or boundary conditions, but it does contain an artificial neural network, right? So same thing as just a normal neural network, but I'll call it ANN as we go through. Now that contains the usual adjustable parameters, so biases and weights, system of weights and biases that will fit points that you'd sample from the domain of whatever system you're looking at, right? And then they say, hence by construction, the initial conditions or boundary conditions are satisfied and the network is trained to satisfy the differential equation. They compare a series of model problems. The paper's about 20 pages long, but it's very readable. It's kind of nicely laid out. And they compare all their methods. Well, they compare their method with the finite element method. So most people are probably a lot more familiar with the finite element method. Is probably what you jump to straight away if you were solving differential equations. And yeah, so I'll do a bit of an explanation of each of these things when we get to them, just because I assume no background knowledge really when we're going through this. So the advantages that they say, and this is the huge one, and it's probably the one that takes the most kind of getting your head around, that they say their method offers a differentiable, closed analytic form that it can be used in any subsequent calculation, right? So that's obviously going to knock most other numerical methods aside, because as we know, most other techniques offer discrete solutions or limited differentiable solutions, okay? Which may or may not cause a problem. You know, it's context specific, so that might not cause a problem depending on the problem you're looking at. But definitely differentiable closed analytic forms are to be desired. The number of model parameters is far less than any other solution technique, right? So they say specifically when we get to higher dimensions, other numerical methods can become intractable, can become very difficult with the number of model parameters that you need to implement, especially if you're gonna look at points, very fine points around certain areas of your domain. They say that their model parameters are far less. So these are all claims that they make. Universally applicable to ODEs, systems of ODEs, systems of PDEs. They have examples of everything. The problem is that going through the examples that they have of more complicated systems of PDEs, the equations get quite messy. So I probably won't do that. And they say this can be implemented on parallel architectures, which I won't really come back to, but they do have a justification for that in their conclusion. Right, so background to neural networks. So this isn't in the paper, but I thought it would be useful to introduce. A neural network is a system of weights and biases that takes an input vector X we have here, which are certain points, and aims to produce outputs based on a cost function, right? So here we've got a neural network with two hidden layers. The bias terms are indicated by the +1 at the bottom. There's lots of ways of drawing a neural network. And what makes these neural networks the most useful is the presence of the activation function, okay? So here's what happens at each neuron in the network. An affine transformation, Wx plus b, so the weight matrix is multiplied by the input matrix. So that's the original input in the first layer, in the input layer, but in every subsequent layer, that'll be the inputs coming from the previous layer. Plus the bias is performed. And the most powerful thing is it's followed by a nonlinear activation function. So that's what separates it. If we didn't have that nonlinear activation function, then this whole network will be equivalent to linear regression. But the nonlinear activation function is the key to it. Traditionally, most people use the sigmoid activation function, but most people now use a ReLU activation function, which is a rectified linear unit. It works really well. It's just the max function between 0. So the input, it's the max between 0 and the input. So it's like a horizontal line until the y-axis, and then comes up at a 45 degree, or comes up at an angle anyway, and it it works really well. Okay, and then to train the neural network, so what you do is randomly initialize all the weights and biases, and then perform gradient descent. Here we see gradient descent with 2 parameters. You're going to have a lot higher dimensional gradient descent, but it'll be harder to visualize. And the system is called backpropagation until the optimum value that minimizes the cost function is found. Right, so in our examples later on, we're not going to be able to visualize the gradient descent like this, but it's useful to get an idea of for this. And you can actually have more complicated gradient. You can have more complicated ways of finding the overall minimum, but this is okay for explanation purposes. Right, and why these authors, they allude to this as well. Why they decided on using neural networks for this task is to do with the universal function approximation theorem. I copied some of the article of Wikipedia on it just to show. The original paper is dense, and most people don't really know it by that. They know it by what's at the bottom. Neural networks with a single hidden layer can be used to approximate any continuous function to any desired precision, right? So that's very powerful. It doesn't mean that it will perfectly replicate the function, but it means it'll approximate it very well. Right, so that's their justification for for their approach. I've taken the very first example from the paper, and I probably should have taken like a middle example from the paper because this one is quite straightforward first order ODE, but I'm a little bit constrained by time. But in the discussion afterwards, I can open the PDF of the paper and we can talk about more examples. So if we consider this first order ODE, where we have psi of x, first derivative of psi of x is equal to fx psi, and x is on the domain 0 to 1 with that initial condition is equal to a. Right, what they do is form their trial solution, which is the first part, which, as we've seen already, satisfies the initial condition, and the second part, which is going to be a trained neural network, right? So what did I say here? Where nx and the vector p is the output of a neural network with one input unit x, and the so that's a vector x of points on the domain 0, 1. And the parameters p, so that's your weights and biases of the neural network. And as you can see that psi of x satisfies the initial condition by construction, because at x is equal to 0, we're gonna have our initial value. Okay, they convert this into, so these equations they have written out in a far more general sense, which I can also show you, but they look a lot more complicated. So specifically for this problem, what we have is the minimization problem now to be solved, which of course is just equation 1 up there, more or less rewritten. Okay, so you're gonna have the mean squared error up there. And yeah, so I didn't actually put in all the details about what happened in equation 4, right? So they do, what they do now is compute the gradient of the error and do gradient descent to find the minimum of their neural network. We can jump back at the end, and that's really the whole key to this method. But the equations get quite messy there. Usually they don't actually show further than that when in the paper. So that's probably a negative of the paper as a whole. Once they get to that point for each of the examples that they do, they leave the rest to the reader, which is a little bit annoying, but I can show everyone who's interested at the end the rest of their method from there. What then they compare each of them to the finite element method. So the finite element method is an expansion of piecewise continuous elements. People are probably a lot more familiar with the finite element method, where we have basis functions, and there's an isoparametric mapping onto a computational domain, and we use the Galerkin method to minimize the weight of residuals at each nodal position. So here's the more kind of involved examples that Lagaris, he was the main author in the paper, that he presents. 5, 6, 7, 8. So there's systems of kind of increasing complexity, or their equations of increasing complexity, including a nonlinear PDE. Okay, and for each of these examples, he has a little paragraph written out. Not sure if it's good to jump back as I go through each of these examples or wait till the end, but I'll wait till the end for now. This is our first journal club. There's always going to be teething problems. And what's presented is the PDE and the trial solution. And then it's the rest of it just follows the usual steps, okay? And in each of those cases, so for 5, 6, 7, 8, he has, so when you're doing kind of machine learning, you're going to have a training set and kind of a test set like this. And for each of these points, you'll see the neural method. So this is the method that they have compared to finite element method. It performs way better. So you want to look at ones that generalize better to the kind of the trainings or the test set here. And you'll see that each of these are performing, and surprisingly, these results, everything in the neural method, it performs equally as well in the training set as the interpolation set. But you'll see for finite elements that it always performs worse on the interpolation set. So this is the maximum deviation from the exact solution for the neural and finite element methods. Even though sometimes the finite element method might perform better than the, and actually probably in every case there, performs better on the training set, it doesn't perform better on the interpolation set. Right, so what they conclude is that the method exhibits excellent generalization performance, that the deviation as test points was no greater than the deviation at the training points, which is the key, which is the big kind of output from this paper. It can easily be extended for dealing with domains of higher dimensions, which isn't the case for some other numerical methods. They actually didn't play around with the network architecture, which is very unusual. Usually when you have papers with neural networks, there's a lot of work done on optimizing the hyperparameters of the network. So you can leave all as variables, the number of layers, the number of neurons in each layer, the activation functions. You can try everything you can think of to try and get it to minimize more, but they didn't do any of that, which people have done since then, because this paper was 20 years ago. People have done a lot of that since then. And their training grid points were selected equidistantly, which they said was a bad way to do it. They probably, a lot more sensible approach would be to select more training points at regions where the error values are higher. And yeah, just to conclude today, for the presentation part anyway, I thought it was a really nicely written paper, and I've heard lots of people make reference to it at other talks on machine learning, which is what really attracted me to it. I like that it kind of starts with the more theoretical approaches and then moves on to the more practical examples. As I say, I'm not 100% an expert on this paper, but the parts that I did get to were really nice. I think probably they could have done a better job at placing the results in context. The way they present it is as if it's a fully kind of, it's an approach that they thought up with originally that came to them. And I wonder, is that actually the truth? There's probably a bit of creating a narrative there for themselves. I imagine there was probably approaches done to this beforehand. And what most people discuss after they've seen research in this area is when would you want to use other numerical methods? You know, if this approach, as they claim, can provide in general differentiable closed solutions with lower errors on unseen points in your domain, then it seems like it's going to make some of the other numerical methods more redundant, but that's a discussion topic. I'm sure people have strong opinions on that. I'm not one way or the other. And this is the references. That blog in the middle is actually quite good. You can run some code examples from the paper and really get a feel for them, because I think this is one of those examples where you really have to kind of just run through the code yourself to get a feeling for this method. And that's the original paper there on the bottom. And that's all I have for today.
Hi guys, welcome back. I just wanted to provide a little bit more additional material in addition to what we already covered in the main part of the journal club, just because we brushed over some of the finer details, and I'd like to go back into a little bit more detail now, which came up in our subsequent discussion afterwards. So here's one of the problems that they presented in the problem section of their paper, right? So they call this problem 1. It's an example of an ODE, which we have there in equation 6. Okay. Now, we have an initial condition with this equation, which is psi of 0 is equal to 1, and our domain is x is on 0, 1. First step here, we rearrange, and we get the form of equation 7. So the whole right-hand side of equation 7 is going to be what we call this function f. All right, now that's useful shorthand for when we delve a little bit deeper into our method, to remember that on the next slide. Okay, so as we proceed, this is what they've encountered already in a general sense. Of course, here we're talking about something a little bit more particular. So what we have is a trial form of our solution, which I will denote here by psi trial. Psi t was what was given originally. I find that a little bit confusing, because sometimes you can kind of overlook that as being something to do with time, but here they mean a trial solution. And the first part, so the 1, fits our initial condition, and the second part is what's going to be our neural network. Okay, so our loss function, as before, is going to be given by equation 9, which is we're going to train our parameters of our neural network to minimize this function. Okay, so it's the derivative of the trial solution at each of our xi points, so each of our input points. Difference between that and our f, which was the whole right hand side of our equation on the previous slide. Okay, so the derivative of the trial solution we get from equation 8, and it's fairly straightforward. So that's just given by a product rule. So this first equation here, this derivative of our trial solution, we get by fairly elementary derivatives. And the second part here, so our f function, is going to be the whole right-hand side of our previous equation. So it's going to be this long, messy right-hand side with our new trial solution of psi. Right, let's look at then what they get. So we tidied up then some of the questions afterwards were on what form this loss, what this loss function actually was what we were looking to minimize with this loss function. So hopefully that clears things up. And finally, what we have is, I just took one of the graphs from the original paper, which was about problem 1, the accuracy of the computed solution. So this figure shows the deviation from the exact solution at each of the grid points. So they're the small circles that we have up here. Okay, so each of these points up here are the small circles. So there were the inputs to our network. And the deviation at the other points is given by the dashed line. So our original domain was only from 0 to 1. Okay, but what we actually see is some points outside of the domain, and what the authors noted was that the extrapolation error out here actually remains low for points near to the equation domain. So in particular, when we see from about 1 to 1.2, the solution is still quite good. Of course, outside of this domain, our solution deviation increases dramatically. But inside the domain, we see near perfect correspondence between the computed solution and the exact solution.